Hello, welcome YouTube. Welcome back to our videos on turbulence modeling. So in the last video, we talked about Germano's identity and how it applies to this doubly filtered equations, so that when you separate out the terms as you do so here, you can bring it over to the left hand side or right hand side, sorry. You bring it over to the right hand side, and what you'll get is something like this. And how do we model this tau IJR? That's usually done with a turbulence model over here, where you have tau IJR minus this thing over here, minus this thing over here, which is the 1/3 of this. This is the average of the diagonal components. So just recap what these are. Okay, I think I should put it here like this. Yeah, that's the right one. Yeah. Okay, it is something like this. Alright, so tau ij r minus 1/3 tau kk delta ij. So there's a summation here, there's a summation here, and there's a summation here. So basically you take the diagonal elements of this matrix, and then you do a 1/3, you divide them by 3 and you subtract them off. If these averages become 0, then tau IJR and the deviatoric part is actually the same. But remember, yeah, we want to model the deviatoric part, which is us so-called like subtracting the so-called pressure acting on this system. Yeah, and we model it using this strain rate tensor and the new SGS, which is the subgrid scale viscosity. Okay, so what is the subgrid scale viscosity? Just to recap again, it's C Smagorinsky times the filter width. You square it, and then you multiply it by this mean rate of strain. So the mean rate of strain is this, where Sij is as follows here. Alright, so if you were to just substitute the expression for viscosity back into this equation, you will get something like this over here. So basically what we did is just to take this and we substitute all of this in here. Okay, and that's what we are doing. Then you'll get this expression over here, and this is actually just a direct copy. Oh, yeah, it's not a direct copy. We can bring the C Smagorinsky out, then you get the C Smagorinsky squared. And this, well, in our model here, it's actually dynamic. It is dynamic. So this constant is a dynamic, so that constant. So that means it's always changing. We sometimes like to replace this by CD. So this is what you will see in literature. Of course, one more thing I want you to be very careful of is this row over here. Sometimes you'll see online where people model this using a dynamic viscosity, as you see here. So for example, if you take a look at the Smagorinsky model here, okay? Yeah, the Smagorinsky model here. Yeah, you see the Smagorinsky model here. When you see this tau ij minus 1/3 tau kk delta ij, you get 2 into cs delta squared S, the mean rate of strain, then Sij. Mu SGS equals to rho blah 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 blah. So you see here is the kinematic viscosity here. Sometimes when you associate tau with, we usually do it with dynamic viscosity. So to differentiate both, if you want to make sure it's dynamic, you should put you should just be clear to yourself this is a dynamic thing. But otherwise, this is how we would normally write our stress tensor, so to speak. Okay, it should be without this row over here. Okay, so every time if you're talking about a dynamic shear stress, I will put dynamic here. Otherwise, we should use this notation where this is like a so-called the dynamic shear stress divided by the density. So this is how we actually deal with the deviatoric stress. So now we can deal with Lij in a similar manner. So remember, the dynamic part of the stress is like so, and then the kinematic part is like so, and I'll always be using the kinematic part from now on. So which is the dynamic shear stress divided by the density, and you will get expression like so. And we try and do the same thing to Tij as well. So Tij, remember, this is actually the difference, or you see in a Germano identity here, it is Lij plus the filtered part of the whatever stress that is, the subgrid stress tensor. Okay, and remember, this thing is filtered, so it's slightly different. Okay, so we do it, we say it is the same, except that the stresses, the strain rates we use inside are doubly filtered. So instead of S, we have a S bar, we have a S bar tilde, and instead of Sij, you got Sij tilde. So if you apply the filter over, if you apply the filter over Sij, then you would see this this part. You'll see U being filtered twice because you do the linear rule. So if you do a filter over this whole thing, it is the same as doing a filter over this and over this individually. Then you see, this differential, you can bring the filter inside, because that has nothing to do with the filter variables. So that's one of the rules. So we can bring the filtering inside, and that's how we get our expression there. Then naturally, the analog of this mean rate of strain, S bar, we have a filter on it as well. So what we will have is just simply this. We will have the two filtered strain rates in there. Okay, so this is how we get our deviatoric expression for the deviatoric tensor for this Tij, capital Tij. It is this one. Alright, so we substitute back into our Germano identity, which is like so, which is this. So Tij is, well, we just copy and paste this one. We copy and paste it in here, and then the tau ijr, you'll just copy and paste this thing into here. So of course we need to take note that we are modeling the deviatoric part of this big Lij. So remember that we need to subtract this deviatoric part just to make it consistent, because when we model this kinematic viscosity, it is subtracting this deviatoric part. Likewise, the same here and the same here. Okay, so when we substitute in, we will have this over here, and we will have the this over here is actually this Tij. This over here is actually this tau ij. Okay, or rather, if we do it like so, let me not skip too many steps. Alright, I will do this, and I'll have the Tij minus 1/3 of this. Alright, and tau ij tau ij we minus 1/3 of this. Alright, remember that's just taking the off diagonal elements, or rather making all the off diagonal elements 0, and then the diagonals are just the sum of the three elements here. Okay, that's all that this matrix is. So I'm taking this as these three, and I sum over here, and I put it in the first row, first column. second row, second column, third row, third column, divide by 3, and subtract. So that's all that's happening here. Then I'll put, usually, yeah, this is our equation for this Lij, the deviatoric part. So sometimes we don't want to keep writing all of this. So in literature, you usually see this alpha ij and beta ij. So that's just a short form truncation so that you can see which part depends on CD and which part doesn't. Because remember, the part that we want to deal with is CD, and the whole point of doing all this double filtering is so that we can get a value of CD for that region. So to isolate the CD out, sometimes it's easier for us to compress these two into something that's neater. So alpha ij equals to this messy thing over here, beta ij equals to this messy thing over here, where alpha aj is everything that I'm highlighting here in Tij except for the CD part. Likewise, beta ij is everything in here except for the CD part. So I'm just taking the CD part out so that's easier for us to see and deal with. Okay, so this is what in literature you will normally see. So when you see something, an expression like this, it is actually the same expression as what you see over here. This alpha, it's over here, corresponds to this beta, it corresponds to this. Alright, so next problem, next step is to try and take this CD out. You want to factorize CD out so you can start to isolate it. Okay, so you want to bring this CD out here and this CD out here, right? So to bring both of them out, we need to make an approximation. Okay, so we need to make an approximation. So this should approximately be C, D, and then beta, ij, tilde. Alright, so that's all. We make that approximation by assuming CD is constant with respect to the filter, or rather, the right way to say it is locally constant so that within the filter, is the value of CD doesn't change. Alright, how does this look like? Well, okay, let me erase and do it again here. Okay, so let's say you have a CD that varies with X. So this is the axis, and then you kind of have CD going up and down like so, very random. So let's say your filter width is this much, and you want, to find a representative value of CD. What you do is, assuming CD is constant, you just take an average of all the CD values here. It could be like by taking the area here and the area here, you try and make it equal. There are many methods of averaging, but the idea is that you get one average CD. Average CD. Okay, you get average CD, and that will be your CD for this filter width. All right, for this filter width, and this is the test filter width. Okay, so that's what we are seeing here, and that's an assumption we make. So we can approximate this messy term here, and we bring the CD out. Okay, and so that we can approximate this left term as this right term. All right, they're not exactly equal. Of course, there will be an error. Okay. Okay, so yeah, basically just to recap, what are we doing? We said that we have this special tensor over here. All right, and then we model them. We model this tensor using this Tij, the deviatoric parts of Tij and tau ij. This will be directly linked to our viscosity equations and our mean rate of strain, or the filtered rate of strains. So this one's the filtered once, and this one's filtered twice. Likewise over here. Okay, so yeah, that's what we are doing. Sometimes, and then we just to simplify this, we introduce alpha ij and beta ij, we get this. And yeah, the idea now is to isolate CD, because you want to calculate CD. That was our goal. So we have to isolate it out by making this assumption, so that you know, the filtered part, we assume that this is the filtered part. I mean, this is constant with regards to the filter, and we can sort of bring it out. So we can bring this part out, and this part we kind of just leave it inside the filter. And we can then say that this Lij minus 1 over 3, the deviatoric part of Lij, equals to this term here minus this term here. So it's approximately equal. So of course the caveat is that CD is not truly constant with space. We need to find an average CD which best fits the equation locally, i.e. within the filter. So that's what's happening over here, where we, within our filter width, we assume there's an average CD and we try and calculate it out. Okay? Now, how then do we find CD? So we try and find an average CD, remember? So yeah, I use that average term there to say it's average, but yeah, we are trying to find this average CD here, and we know the filter width of this, and then we will for sure know this because this is our filtered rate of strain. So is this. These are all based on the resolved velocities, because if you take a look over here, these are resolved velocities. This is something we can calculate out with Navier-Stokes, and this will be fitted here. So all these terms here, alpha and beta, these are known. Then the only thing is that this thing, how do we calculate the exact value of this Lij, or the deviatoric part? So how do we do that? We need to take a look at our original Germano identity. So this is Germano's identity here. Okay, so we have, okay, how do we find CD now? So we have Germano's identity over here. And then, okay, how do we have these terms? So recall this. Where did we get this Tij from? So Tij is or rather the Lij. Where do we get this Lij from? So remember when we were trying to decompose our doubly filtered product velocities. Okay, I don't know what you call this. This Uij bar, Ui bar, Uj bar, and you filter everything. You can break it down into these three terms. First, or these four terms. First is the the product of the doubly filtered velocities here. Then you have the so-called doubly filtered, so-called like Leonard stress, something of the analog. And the doubly filtered cross stress and the doubly filtered Reynolds stress. Okay, and these three will constitute this script Lij as shown here. So what is Lij? Lij is actually equals to, okay, Lij, however you arrange these equations, Lij, all right, if you bring this part over to the left, you see that Lij equals to Ui bar, Uj bar. You tilde it, means you filter it a second time. Then you have the product of the doubly filtered velocities. So Ui bar and tilde, Uj bar and tilde. And having knowledge of this, we can easily compute the deviatoric part. Okay, so remember that we are just going to take the so-called diagonals, sum them up, divide by 3, and you subtract. So we have this. Remember what this matrix looks like? It is over here. Yeah, it is over here. So if you only know this part, we can sort of derive this part out by just taking the diagonals, sum them up, and place them in the diagonal parts of this matrix, divide by 3, and we subtract off. So this is how we get this deviatoric part. Okay. So if you know this, you will know this, and then you can find this value here. And roughly, you will have one equation for CD. So CD, you can approximate it as this term here, this term over here, which you will just compute using the difference of these velocities here, and then you do some addition to the matrix. You edit the matrix a little bit to make the deviatoric part come about. And likewise for this part also here, over here, will be the subgrid stresses, the doubly filtered subgrid stresses, and the singly filtered subgrid stresses with this filter on top. All of these you will be able to compute to get an approximate value of CD. And you're almost done with this dynamic model. I mean, that's the key idea. So we have an equation for CD. Now the problem is this: depending on which element of the matrix you go for, there are actually multiple values of CD depending on your index of I and J. Because remember, in this matrix here, there are actually multiple what do you call that? Multiple values being stored in this tensor, so to speak. Likewise, there are multiple values being stored in this rate of strain over here, for example. Okay, so you have this kind of issue where, all right, I need to have a single value, but now I have multiple values of CD depending on which element of the matrix I use to compute these values. So we do need to take some sort of an average to find this CD, and this is not the same average as the one that we have here to approximate, but this is an average. This is an average across the matrix. Okay, so all right, so from here we have many average CD guesses. All right, we have many average CD guesses, and that's done using the complicated formula you see here. That's done using the complicated formula that you see here. Okay, never mind. Okay, so based on this formula, you have many averages you can guess. It can be an average over here, the average can be over here, the average guess can be over here. You don't really know. So this will give you multiple guesses. Guesses of CD average. Okay, this will give you multiple guesses of CD average. And now the thing to get your final guess, you have to average the guesses. Average the guesses. Okay, so that's the next step to calculating a so-called final value of CD. So how do we do that? We're going to discuss that in our next video. So yeah, that's basically it. I mean, the rough concept is there for you to see, that we use this double filtering so that we can get a CD out which is based on the filtered velocities that we know. That's the hard part. Now, slightly easier is just to find slightly easier part is just to find an average of all these guesses which they are given to you based on these filtered or doubly filtered velocities. So that's all I have for you. Thanks very much. I'll see you guys again. Thanks for watching. Bye-bye.